All right, this is the lesson 9.5 supplement that goes before the actual lesson 5 material in the book. I thought I would give you this to help you just focus your understanding of why the alternating series is what it is. And it will also lead to something called an error approximation that you'll be using in lesson 9.5. Okay? So I've got here as an example of an alternating series, the sum of n equals 1 to infinity of negative 1 to the power of n plus 1 over n. I'm going to ask you to write out the first 6 terms. Okay? So I plug in n equals to 1, so the answer is positive. This will be 1 over 1, so that's just 1. This is an alternating series, so the next one's negative, right? If I plug in n equals to 2, I'll have here 1 over 2. If I plug in n equals to 3, I'll have here plus 1 over 3. And then minus 1 over 4 plus 1 over 5, and then minus 1 over 6. Okay, those are the first 6 terms of this alternating series. Of course, it continues on, so plus dot dot dot. Okay. Why is this an alternating series once again? Can you tell me why? What are the 3 characteristics? You'll notice that the terms alternate. Good. You'll also notice that the terms never increase in absolute value, or they always decrease, right? And then the third thing we're supposed to check is the limit as n approaches to infinity. And definitely, if I were to look at this, it doesn't matter what that is, that's just positive 1, negative 1, divided by a huge number, this equals to 0. So all 3 things are satisfied, definitely. Okay? So by the way, you also know that this will be a converging series. But I don't really want to worry about that right now. Okay, I just want to look at what I call the partial sums. I want to look at what happens if we sum just a few number of terms. So when I have this thing called s sub 1, that means I want the sum of just the first term. Well, that's pretty straightforward. It's just 1. So if you think about it, I'm starting here right at 1. Boom. Okay. Now look what happens when I ask you to find the partial sum of the first 2 terms. So that would be actually 1 take away a half, which of course equals to a half, or 0.5. So in essence, what you did is this. We started at 0, we went all the way to 1, boom. But then I had to take away a half. I have to subtract a half, boom, and you're left here at your answer. Okay, so this is where s sub 2 is. Okay, that's s sub 1, s sub 2. Okay, let's keep going. What's s sub 3? The partial sum of the first 3 terms. So now I'm asking you to do 1 minus a half is a half, half plus a third, that's I think 5, 6. So that's approximately 0.83 repeating. And so what happens here is you're starting at 0, you're going to 1, and then we have to subtract a half, and then we have to add a third to give you like right about there, 0.83. So now this is s sub 3. Okay. You see how I'm doing this alternating nature, right? Going further to the right, then coming back to the left, then going further to the right. So now if I did s sub 4, yes, we'll do this a few more times, and if you can do this ahead of me, go right ahead and do that. This would be what, 5, 6 minus 1 quarter. That's, I think, just 7 12, I believe, which is 0.583 repeating. So here we go. Whoop, whoop, whoop. And then now back minus a quarter. Whoop, to about here. S sub 4, 0.583. Should I do one more? Let's do 2 more. So 1 minus a half plus a third minus a quarter plus 1/5. And you're thinking, I don't even want to do this anymore. Fine, I'll just give it to you. This is 47 over 60, which is 0.783 repeating. And yes, I'm going to ask you to draw this again. Whoop, whoop. Okay, maybe I should make a bigger curve. So I have more space to do this. Whoop, whoop. Then what do I do after that? Oh, whoop. And back here, whoop. And then now to 0.783. So whoop, boom. Here is S sub 5. And finally, I'm not going to write this out for you. I'm just going to say dot dot dot. It's equal to 37 over 60, which is approximately 0.616 repeating. So last one here, we go whoop, whoop. and then back here, whoop, and there's S sub 6. Now, I hope you got tired of drawing those things back and forth, back and forth, back and forth. There's a reason why I made you do that, because I didn't want to get you tired, but I also want you to understand this. Each successive term in the sequence of partial sums is always between the two previous terms in the sequence. Do you see? S sub 6 here, this answer is between the previous two terms, right? S sub 5 up here, right, is between the previous two terms, right? So thus, what you can see is that the actual sum, okay, the actual infinite sum, that's just S, not S sub whatever, but the actual sum must be between any two successive terms as well, right? I'm going to be going back and forth like this, boop, 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 and hopefully converging on the actual sum. So we've seen that, for example, the actual sum could have been between the fourth term and the fifth term. Or I could see in the last example here that the actual sum is actually, what, between the sixth term and the fifth term. So in general, what I want you to understand is that sum is going to always be between two terms, either like this or like this. But it's definitely going to be between two partial sums or two successive terms. Okay? Now, knowing this, let me show you what it looks like if I were to actually plot the partial sums. Okay? So this dot here is S sub 1. What's the sum of the first term? Here's S sub 2, the dot that shows the sum of the first two terms. And here's S sub 3, S sub 4, S sub 5. And can you see how it kind of narrows, narrows, narrows? So you know that the actual S must be something in between these dots. Okay? So if I were to generalize this, and I considered any type of alternating series here, my computer just froze. Oh, I can't use my pen. Hold on. Brutal. Let me try that again. Considering I have this alternating series, once again, it's positive, then negative, then positive, then negative, and go on forever. Okay. What you will see is the following relationship. I want us to actually visualize what goes on between the actual term and the actual partial sums. Okay. Um, oh, I guess over here I was saying the alternate series test. Yeah. We've done that before, right? For the alternating series test. Yeah, this is not less than 7.6. That's a mistake. It's less than 9.4. It's those three things, right? Alternating terms, decreasing, or I'll say terms never increase in absolute value. And also the last one, right? The limit and approach to infinity of the term must equal to 0. Okay, so they meet. That's why this series converges to a number. All right. Now, once again, I wanted to talk about this, the relationship between the term, the sum, the partial sum, sorry, at n, and the partial sum of n plus 1 terms. Okay, now, there's actually two different cases here. So if n is an even integer, that means the nth plus 1 term value is a positive value. So what I really mean by that is this. So s sub n, let's say, is over here. Okay? And I know that because the nth plus 1 term is a positive value, I'm going to be adding something. I'm going to be adding the nth plus 1 term to give you the sum of the nth plus 1 term. Okay? Now, in this scenario, this is what I have. And what I'm saying to you is, look, that S, the actual sum, has to be somewhere in between. Okay? Somewhere in between. Okay? Now, I don't know where it is, but I do know that the difference between S and S of n, so S minus S of n, this is what I would call my error. Right? Like, I don't really know how far it is, but I know it's somewhere in between, but I don't really know, so this is the error involved. Now, what is the actual upper bound of my actual sum in this case? Well, my actual sum is, you're right, somewhere in between. So the upper bound really is my S sub n plus my error. Now the question is, how big is this error? And I don't know how big it's going to be, but I know how big it could be at most, because it could be only as big as the actual value of the next term. So the largest this error could be, the largest this could be, is actually a sub n plus 1, okay? Which is really the value of the next term. The value of the next term. Okay? That's what I want you to understand. So the lower bound, well, what's the lower bound? Well, yeah, I mean, the lowest it could be is just s sub n, because that's what we started with. Okay? So that's the situation in this case when n is an even integer and the n plus 1 term is a positive value. Now, you could have this other case where n is an odd integer, so now we're saying we've got some sum of, let's say, 5 terms or 7 terms or 9 terms, and now the nth plus 1 term is a negative value. So if that's the case, notice I put s sub n towards the right-hand side, and now we would know that our next term, a sub n plus 1, is negative, pushing it backwards. And so my sum would be s sub n plus 1. In this case, the next partial sum is actually smaller than the previous partial sum. Now in this situation too, we know that s, the actual sum, is also somewhere in between. And the difference here between s and s sub n, which I better put an absolute value on this time because it's less, right? This is what I want to call the error. So I guess I could put an absolute value here too. Okay. Now in this scenario, what is my upper bound? The upper bound of the actual sum, well, I know the largest it could be would be s sub n. Now what about the lower bound? Yeah, it's going to be s sub n subtract my error. Now, how big can the error be? What's the largest that could be? That same idea that we had over here. The largest this could be is a sub n plus 1. Same business here, okay? So this error, really the largest it could be is also a sub n plus 1, or the value of the next term, okay? So in these diagrams, it really shows that the error, which is once again the distance between the actual sum and the partial sum, must be smaller or shorter than the distance that's represented by the next term. So I'll say smaller or shorter than this a sub n plus 1, right? In both of these situations here, notice the error is always less than the value of the next term, okay? Thus, this gives rise to the idea that the alternating series remainder, or what we call the error bound, like how large is the error in your approximation to the actual sum, okay? That's the alternating series remainder. Well, what is this? Well, it has to be less than or equal to the absolute value of the next term. Why the absolute value? Because once again, I don't know if it's going positive, going to the right, or negative, going to the left, but we know that the actual distance has to be less than or equal to that next term value. So how can I write this in symbols? The alternating series remainder, alt series remainder error must be less than or equal to the absolute value of the next term. All right, and that's the idea I want you to take with you as you now hopefully watch the lesson 9.5 video. See you there.